Hello and welcome back. I'm sure you would have enjoyed that little break to go for a drink or whatever, and you're comfortable now. So let's continue to learn what it is left here. So, to do the learning, what I mentioned earlier, you need to go to one of these site, which I will share this link. I already shared this link in the Facebook group, but also I'll share this again. You need to go to gcc.gnu.org slash online docs slash gcc slash index.html. You please note this down and write it down in your notebook so you know where to go. So I'll give you just few seconds. So please copy down the address of the site and then hit enter. Once you hit enter, it prompts you to GCC command options. Since we are working on ARM Cortex M4 series, you have to navigate down all the way to 3.19.5 ARM options. So click on ARM options, and this will take you to this window where you will see. I'm trying to get this to look bigger. Okay, that worked. So we are on 3.19.5 on ARM options, and this is what you want. MAB ARM, MAB frames, and different things. So what we really want from this is we need the name Arch architecture name extension, and the next one is architecture name, and there will be mCPU and mtune name. I'm scrolling for that since I expanded. There it is. We need mtune name where it shows and specifies the different versions and different microcontrollers, and the name we are after is we are learning Cortex M4 series, so that's the name we are after, and we got to use mCPU name as the extension. Extension is Cortex M4. So both are more or less the same. So we need to go here and copy this, and we have to use this in our command prompt. So once you are here, note down the name and the extension. We are doing this why? Because we need to target now that main.o file that we just generated to be target specific. So we are learning STM32F411 RE nuclear board, and it's a Cortex M4 series board. So we have to make that as a target, and you need to write that program to compile so that it is for this target board and not a generic board. Okay, so that's why we are doing this. So now let's go into the command prompt and type this. As you read from the session 4 about the ARM architecture, the ARM comes with two different modes. One is the thumb mode and the ARM mode, and Cortex M4 comes in the thumb, as you know, by default. So I don't have to worry there. And now let's go to, as you know, M-thumb, the ARM Cortex M4 comes with the M-thumb, and also the other mode is M-ARM. Okay, so come here to the command prompt. I'm going to clear the screen. To clear the screen, the command is CLS, clear screen. That will wipe off. So just to give you a good blackboard view so I can type and you can follow. So that's why I just cleared. So if you want to clear, type CLS in your command prompt window, and that will clear the previous ones and will start new. So here I'm going to call that same program that we used on the example 2. Example to, we are in src. So here I'm going to make the main.o file into a target specific one. So to do that, you need to type this. If you press the up arrow, you will get the previous command. So it helps you to reduce the time for typing. If you work in multiple complex projects in the real industry, believe you me, having all this already there, it saves a lot of time. So if you press the up arrow on your keyboard, it'll get you there. So we're going to use this and change a few different changes. So left arrow, go to -C, and we're going to include the Cortex MCU. So MCPU, this is the one we got from that site. This is, we're going to set target specific to Cortex M4 and space main C, and you're going to see the object files. And also you need to say what mode it is. So you need to say it is a thumb mode, then space, and then go and hit enter. We need to create the assembly program. So I'm just creating .s and hit enter as soon as you type. So it will take few seconds to create that file, and once it's done, it will come as with that, and then type dir to see the created directory. So now we can see the main.s, the assembly language that I just generated. It just created at this timestamp with the file name main.s. So that's how you create. Remember, in IDE you just go there and right click and copy and change names. So likewise, this is the command prompt command that you have to type in to create a directory file. So these are all the directories that you have to create. So that's generated. Main.net, right click, open with notepad, assembly code, this is the C program. Okay, so the next step is to, we're going to analyze what's in there in the main.s program that we just generated. To do that, you need to main.s. So now you generated this. So if you go to the folder where it currently lives, as if you remember, we started with just main.c, syscalls.c, sysmemc, these two directory we just created. From the last command main.o, this created. From this command main.s, the assembly language is created. So I'm just opening to show you what's in there with the notepad, so you would get a little bit more understanding about what it has. Notepad. It's a tool chain. This is the notepad. For some reason I can't open that notepad file. It doesn't let me. Why don't you let me to open? Right click, open. There it is. So this is the file that you saw in online GDB. So this is all machine created language. The one you would be able to read is .txt, .data, .bss, .ro. You will get to learn all of this shortly, but this is what we just generated, and the tool chain helped us to create this file. So this is what inside main.s is. Okay, let's move into the next thing to learn. So once we are here, now we're going to analyze what we just created. So to analyze what is the command that I used, you have to use object dump. So I'm typing arm dash none dash eabi dash object dump dot exe and hit enter. This will get you to analyze the sections, further sections. So we're going to concentrate in this one the sections, because we're going to learn how we're going to write our own sections. So -h, it displays the contents of the section headers. So this is the one we're going to analyze. Excuse me. To do that, just copy top arrow, and then after .exe space, you're going to analyze the header file. And which one? The output of the header file. So -h main.o, and you hit enter, see what happens. Okay, so this is the object file, that's the executable file. Once you hit that build process, so this is the final file that you end up getting, which you load into the targeted microcontroller. In our case, it's STM32, and this is the file format. It's an ELF format, and it's an little Indian, and it's an ARM. And these are all the sections that it generates automatically. It comes and generates .txt files, and it gives you the size, and the .data, .bss, .arvodata, .comment, .arm, .attributes. This is what we also generated by this main.s. The system got all this .txt, .data, .bss, .arvodata, .comment. So this is what it has. So we are analyzing the sections now, what's inside all these sections. So that's why I showed you how to get to this stage. So this is the way you should analyze any of your compiled project in command prompt. By not using IDE, by using command prompt, this is how you get to see the sections, what's inside your program files. So continuing with the process of build, the process of converting high-level code to machine code. So this is what we just saw, the .c file. First, it goes to the pre-processor stage, where it gives you the main.i, and still it goes to the parser stage and goes into the code generator, and it converts to a .s format, that's the assembly format. The assembly format code takes the assembler, and it gives you the .o object file, which is the executable file. And this can be relocatable, meaning it can be target specified, and it can be moved to hit for any selected target. So the process architecture specifies the machine code with no absolute address. And then it moves to the next stage called the linking stage. The linking stage of the build is whatever the object file that it compiles and gives you the object file won't have any addresses. So the linker puts all those addresses into the object files and comes out as the .elf, the final .elf. This is the executable and debug format. So once again, if you want to convert this .elf file, you have to use this tool called obj copy. You can convert from ELF format to .hex and .bin format. The linker will have the assembler code. So in summary of the build process, we used arm-none-eabi-gcc. It has 3 stages of pre-processing, which is compilation and linking. It's all done by this one command in command prompt. So this is how in the IDE, when you hit the build process, this is what happens. And all you get to see is the .elf file. You won't get to see what happens with the intermediate files and the object files. I just wanted to show you what are all the things that happen behind the scenes. So after you hit that build project, this is the steps it goes through and comes out as .elf. So the analyzing.o files, the relocatable files, the main.o is in the ELF format, which we just saw. So the ELF is a standard file for object and executable files in GCC. It is a file format which describes you to organize different various elements that has both the data and the instructions, and it shows to give you different directions and different sections of that sections, like .txt, .bss, .ro data likewise. And also you can format or change this to other file formats to bin and hex format through what's called COF, common object file format. If you use that, you can convert to Unix platform, and you can use ARM image format for image formats, and there is another one called SRE card for Motorola devices. So these are all just some simple analyzing files. So the compilation and compiler flags that I showed you, where you have to make your main.o as a target specific. So this is the link that I showed you to download, where you get the information of mCPU name and mCPU equals I'll show you, where you have written this mCPU equal Cortex M4 mthumb. So this is where you got that name from here, and you have to copy that and paste it here to create and show your intermediate files. So in order to make a file, these are all the steps you already went through. You have to go to the compilation process, and you have to type this, and then go to your main architecture and make that as a specific file, hit to this Cortex M4, and you need to create the compiler flags by doing mCPU mthumb. This is the one we just did in the command prompt, and you need to create main.o from the main C, and these are all the flags that you need to use. So this is just to make a file through command prompt format for analyzing to relocating the files. So this is how the compilation to object file processing takes place. As in any C program, the machine code which doesn't have any addresses. So the machine code will have the instructions and data. Instructions are stored in flash, as you remember, and the data is stored in RAM. And once you start to hit that build project, it gets into the compiler and throws you at the other end as main.o. The machine code generates that, which doesn't contain any addresses at this stage. So these are all the different sections of the program. As I showed you earlier here in the command prompt, when you do the analysis, through this object dump, these are all the sections you get: .txt, .data, .bss, .ro data, .comment, .arm, .attributes. So this is the one. Before I jump in to show you exactly what they are all in the form of writing the startup code file and getting dissected to the sections, I'm going to just briefly introduce you what they are all and what do they have. .text section will have all the program code. All the instructions will be in .txt. And .data will have all the initialized, non-constant, all the global variables. And .bss will have all the global variables of the uninitialized objects. And you got .const, .ro data, that's read-only data for initialized constant objects, and .c init, it's used for C global variables at the startup, and .stack, as you learned from previous sessions about stack memory, so .stack is used for the function call, and .sysmem for dynamic memory allocation pool. So these are all some of the sections that you will see when you do the analysis. So when you work on a project, when you have multiple files, for example, we learned previously on day 7 or the project that you learned about blinking an LED and controlling the switch to control that LED. So projects like that, it will have different main files or different .c files. For example, you will have a main.c, and when you hit the build, it goes to main.o. Likewise, the LED program, it's written as and saved as led.c. And as soon as you hit the build the project button, the compiler compiles and gives you an object file. And inside that object file, these are all the sections that comes out with .txt, .data, .bss, .ro data in the main and also on the LED examples. So what is the purpose of the .elf? The final .elf, what it does is it collects and gathers all the sections of that particular name. So it collects from the main.o .txt and from the led.o .txt, collects the same file name and groups together and then stores inside a memory location inside the microcontroller under the same name. So these two are different files, but then it categorized and grouped together into one single file called .text. Likewise, it will go and take .data from these two files and then go into ELF and then save into .data, and likewise it goes to .bss. It copies this and gathers both the files and then goes to this location and save it under .bss. Likewise, RO data. So this is how the final .elf happens, and this happens in the linker. You have a separate session to learn about the linker section, but I briefly tell you the final .elf is created in the linker section. The linker is the one, it maps all the .text files and it gathers from the main.o, from main.o and text.o, it groups together and then stores in the particular file name, the same file name, inside the sections of the memory inside the microcontroller. So that's what the linker does. Now let's see what's the final executable code looks like. As you know, these will be all placed inside the flash memory. So inside the code flash memory, this is the structure it will get. Right at the bottom of the code memory, it has the start address and the end address, start address and the end address. The inside the flash memory that sits under the first section is the vector table. The vector table, you learned the other session, what it has is it has all the addresses of the exceptions come by the system or from the internal exceptions or the interrupts from the external. So that's what vector table. Vector table will have all the addresses of that exceptions handling. So once it goes and allocates that and saves that, then it goes to .txt and it saves all that files, and then it goes to .ro data and saves those files, and then the .data, and then it goes to unused code memory and it saves all of those files. So if you take how this transaction happens from transferring .data section, so inside that only the initialized data will be stored inside the program memory. The uninitialized data of the local variables will not be stored in the program memory because it occupies a lot of code space. So therefore, we don't want the local variables to be saved as well. So this is where the real startup hero comes in and jumps in and does everything for us. So the main purpose, the main responsibility of the startup file is to allocate spaces in your SRAM memory so that you can save all of these files into that allocated memory. So the main purpose of the startup code is to allocate memory spaces in SRAM so you can save all these files in there. As you know, SRAM is a volatile memory and flash is a non-volatile memory. And also you would know what is a volatile memory. A volatile memory is when if you do a power on reset or if you do a reset, as soon as it starts to reboot, all the data will be erased. Whereas in flash memory, it will have all its initialized global variables. And if you want to change those global variables inside the flash memory, you can't be using the same because it can't be reused. If you want to reuse those variables again, you have to completely erase all the data and rewrite it again. Same the contents. You can't do simply like the RAM where you can just overwrite it, but if you want to change any variable modifications, then you need to rewrite it. So to do that, you have to copy all the variables, all the data from flash to SRAM. So how are we going to do that? This is the process of the startup. So the representation of copying will start with the data copy. In the data section, everything will have an label to it. What is this eText, SData, eData is? Everything has its start address and the end address. So underscore eText is nothing but end address of the text, and underscore s is nothing but start address of the data and the end address of the data. So likewise, the data is copying from the flash memory and moving to the SRAM memory. So that's where the startup file comes in handy, because it doesn't have to keep all the uninitialized values in here to save space. So that's why startup file creates that extra space in the SRAM, and it copies the data from there and moves to here. So that's the process of startup file. For example, when you create in the global variable a equal to 10, so this is how it is done in the SRAM. In the SRAM, this is the structure. As you can see, data bss heap unused RAM, SRAM, and stack. Stack you already learned from the other session. It's we are using ARM Cortex M4, and the stack model in ARM Cortex M4 is a full descending mode, FD short for. So it goes from the higher end to the lower end, higher end of the address to the lower end. So that's why the stack is up there on the top. And if you need to calculate the size of each sections, because that's where you're going to tell the data, the starting address and the end address. Don't worry, the GCC tool chain that we downloaded will give you that starting address and the end address, and that will by writing the startup file, that will allocate those locations into the data file, and you have a separate session about those coming soon. So the different data, let's go into see what's inside the data. As you know, in the program there are different datas. They are live in the program that related to that particular section, and this is how the data is categorized as global and local. As you already know, you've done your engineering degree, so I'm sure you would be all familiar by now what a local variable is and what a global data variable is, but I'll give you another recap of that. Inside the global variable data, you'll have a global uninitialized data, you have a global initialized data, you have a global uninitialized data, and you have a global initialized static data you have. For example, if you just say int a as a data, it is an uninitialized data, whereas if you say, for example, c equal to 15, that is initialized data. So you initialize, so they live in here. So likewise, the local data will also have all these 4 in there as well. So these data will be stored on different memory locations. So you can also write your own sections to say where they have to be all, So you can dissect the sections, and you can write your own sections, but you have to specify it to the compiler, otherwise it won't do it. So these are all the different data type of a program where the data is categorized and where it actually lives in the memory locations. As we saw from earlier, the global initialized data will be stored in flash memory in load time, and when you do it in the runtime, the startup file takes the data from here and copies and moves across. So that's what it says. Data is copied from flash to RAM. This is the startup code reserves space for this data in RAM, and and um, and it will start to run. Whereas the global uninitialized values will be stored in RAM, and it's in the .bss section, and it always started to initialize to 0. And so forth, like static initialized, it will live in the flash, and static uninitialized, it will live in RAM.bss, and likewise local initialized, it will run in saved in stack, consumed at runtime. Local uninitialized will be on stack RAM, consumed at runtime. The local static initialized will be in flash, and all global constant will be in flash, and these are the RAM. In general, all the initialized files will be in the program memory, and all the uninitialized data will be in the RAM memory. So that's what this table shows here. Now let's move into seeing about each and every section. First, we'll see what .bss session is. .bss is nothing but it's abbreviated to blocks started by symbol and data. So all the uninitialized global variables and the uninitialized static variables are stored in this section, because you can't have that in the flash memory, so it has to live in SRAM memory, and .bss lives inside the SRAM memory, and this is where the uninitialized data will be. The .bss section doesn't consume any flash space as like data section, as I said earlier. So you must reserve this RAM space for the data BSS by knowing its size. That the GCC will tell you, and you're going to limit that space, reserve that space for .bss. Okay. So the importance of the startup file. Whenever you reset the program or start the program, the startup file will always be executed first. That's the importance of the startup file. So say when you power down your board and you're powering off and restarting, that, for example, we are learning Nucleo F411 board. So when you do that, the startup file takes the responsibility to run the program and the startup file first, so that the code will be there and it will be ready to start to run. So the code written in the startup files run before main. So you can say startup files calls the main function. So the startup file generated by the STM, as I will show you later, it will call the main function that you written, will ask it to run. So that's the purpose, the importance of the startup file. Some part of the startup code is target processor dependent. So as I said earlier, you have to make that as the target specific. For this instant, we are learning Cortex M4, so this is the startup code you have to write, and it has to be specific to that. Whereas if you use even a different version of this, if you want to use it, then you can't use the same startup file. You need to write a different startup file, because they're all target processor dependent, so it only works on that particular model, particular microcontroller board. So always go back to the data sheet and verify its compatibility, see where it is capable of, and come up with the startup files. So the startup code stores the vector table placement in code memories as required by the ARM Cortex processor. As we know, we learned from previous sessions, the vector table has all the addresses of the exceptions and the interrupts, and it places in the certain order that we learned from the previous explanation in the sum. other sessions. The startup file also enables you to enable special peripherals in the startup code. Like if you want to enable the floating point unit, you can do so. And also if you want to initialize the SRAM, you can also do so by the startup code. And also the startup code also takes care of your reinitialization. As you learned from previous session, after you run the main program, if you want to reinitialize the stack, you can go there and write a simple code, and that will reinitialize your stack. So in general, the startup code plays a major role and takes responsibility to copy the data from flash memory and allocates a space in SRAM memory and puts the data for usage. So that's what the startup file is, and the initialization in RAM memory. Next, let's see what the vector table placement, how it's shown. So this is the vector table placement inside the flash memory. As you can see, the starting address is 080040, and if you dig deep in and if you see what's inside the vector table, this is what the vector table has. So right at the start of the vector table, you have the main stack pointer, and on top of the main stack pointer you will have the reset handler and then the NMI handler, and then as you learned from the other session, you got 15 exceptions. So these are all the exceptions, and then the interrupts, you got 82 interrupts, so everything will have a start and the end address. So this is how the vector table placement is, and this is generally stored on the flash memory first. In ARM Cortex M4, as you know, there are 240 interrupts, but the one we learning, STM32F411, has only 82 interrupts. So which you can get all of this from the reference manual, as I showed you in previous sessions. I'll show where it is. If you go to reference manual and go to page 248, it is, I think, 248. No, not to reference manual. Okay, I'll just type, sorry, vector table. Is it 198? Maybe 198. Interrupts and events. Okay, sorry. It's on page 198. If you go to vector table, so this is how it's placed. So first, very slow. Very slow. Okay, sorry. I'll go directly to page 198. And if you scroll down, so this is the vector table. The first few locations are reserved, so you can't use it. Then the first immediate vector table is reset. Then after that you have the NMI handler, then the hard fall, then the mem manage. So this is how the vector table placements. If you come to see this is how the most stack pointer value, and then the reset. That's a reserved value for the main stack pointer, and the reset and the NMI, and followed by all the IRQ requests. So as we learned that the exceptions and the interrupts in startup file has 15 system exceptions and the 82 IRQs. So this is how inside the exceptions of the vector table has. First it reserves for the main stack pointer, and then the system exceptions, and then all the interrupts followed by. This you will see in page 198, not 248. It's in a different reference manual. The one I shared, it will be on page number 198. Sorry, I'll just correct that. So 198. So now let's learn how to create the startup file. To create the startup code, the first step you have to do is you need to create your own vector table. To create that vector table, you have to follow these two steps. You need to write the vector table in an array format, so it would be much easier. For example, you saw in the vector table how it is all grouped. It has the main stack pointer as a reserved, and then it has a reset handler, it has the NMI handler, and it has the hard fault, mem manage, bus handler, etc., etc. So it has to be all put in to an array format, which will be like this into an array. You will see that shortly. And then you have to instruct the linker not to include the above array in .data section, but has to be done by the user, and it has to specify that from the user defined section. So these two you have to remember, and let's go into learning about this program. So this is the program you're going to learn, and I'm going to go into IDE and I'll show you step by step about how to write this. Online exceptions, object dump, startup file you're creating. So this is the startup file you create, which initializes .data.bss section in stram, then call main file up. Okay, so I opened sorry, the IDE. I will open the project, open project, open project. I need to stop this. It's in previous program, it's on a debug mode, so that's why it doesn't let me to enter. So file, now you can open a project, close this project, so you don't need this project, exception demo. So now you go to project and you're going to open a project. Or you can do a right click, new. Now we need to file, open file. Okay, I'm going to go by this open file and going to go to desktop where we saved dot this main file. Okay, project. I don't want this file, so I'll close this file. Just give me a sec. Sorry, I'll close this. You need to go general, cancel. Navigation, source system menu. No, I don't want the filter type. I lost the project tree, just one sec. Project, file, import. Sorry, I'm going to close IDE and I'm going to reopen. Just give me a few minutes. It will take a while. Sorry, I'll give you a break. So go and have a short break and come back, and I'll show you how to write this startup file, and I'll explain to you. I'll see you in a couple of minutes. See you then. Bye.